Hi, everybody. Welcome. You're in the right place. We'll get started at the top of the hour in just less than a minute here. Okay, there it is, top of the hour. Welcome, everybody. My name is Alan Barr. I'm with COEH Northern California. And on behalf of the NIOSH-supported education and research centers throughout the country, we're pleased to bring you another installment of the 2025 ERC Ergonomics webinar series, where we offered a free monthly webinars on various topics on human factors and ergonomics. This collaborative effort on behalf of each ERC's continuing education program aspires to provide access to current research supported through NIOSH ERC programs. Thanks for joining us today. If you logged in via your registration email, you'll receive a link to an evaluation form that will qualify you for a certificate of completion worth 1 CE contact hour. I want to take just a second to mention an important event that's coming up July 30th through August 1st, and it's an applied skills in ergonomics workshop, a hands-on training workshop. It's a 3-day in-person workshop that provides guided practice and advanced measurement techniques used by practitioners in the field. The workshop's taught by a team of seasoned professionals, and I highly recommend it. You can read more about that workshop at coeh.berkeley.edu/applied skills. Please take a look. Okay, so, for today's webinar, you will be muted as usual during the presentation, but if you'd like to ask a question, enter it into the Q&A box at any time, and we'll save some time at the end of the presentation to address your questions. The webinar is being recorded and will be made available along with past webinars on the COEH Northern California YouTube channel. Please take a moment to like and subscribe to help us continue to grow that channel. Today's webinar, as you can see, the title, Bilateral Assistance from Active Knee Exoskeletons to Reduce the Difficulty of Occupational Lifting and Lowering Tasks. Our speaker today is Dr. Grace Hunt. Grace is a postdoctoral fellow in the HGN Lab for Bionic Engineering at the University of Utah and the Rocky Mountain Center for Occupational and Environmental Health. She received her BS in Biomedical Engineering at the University of Utah while working as a research coordinator in a motion capture lab and as a teaching assistant for human anatomy. She did her PhD in the HGN Lab for Bionic Engineering under Dr. Tommaso Lenzi, and her research studied the ability of a novel powered knee ankle prosthesis to improve functional mobility for above knee amputees, specifically during sit to stand and stand to sit. As a postdoctoral fellow, she's focusing on assistive exoskeleton technologies during occupational lifting and lowering tasks, and that's obviously what we'll be talking about today. With that, it's my pleasure to hand it over to Dr. Hunt.
Awesome. Thank you so much, and thank you everyone who's here. I'm really excited to be presenting today about this work with active knee exoskeletons or powered knee exoskeletons for occupational tasks. So I wanted to start off by just showing you a couple of devices from the lab that I work in and I've been working in for a while. This first one is a prosthesis that is actually been licensed to a prosthetics company. This is the work that I worked on during my PhD. And we also, at the same time, work on exoskeleton devices. So these are 4 examples of exoskeletons. Here are a couple that assist the hip. This one is the knee exoskeleton that was used in this study. It's been updated a little bit since this circly video was made. And then this last one is an ankle exoskeleton. So exoskeletons that are active or powered or robotic provide assistive torque. So they strap to the outside of your joints and they supplement your joint's ability to do activities by just providing a little bit of extra assistance. So the work in this project is focused on reducing potentially in the future workplace-related musculoskeletal disorders. And most of these musculoskeletal disorders are sprains and strains and tears, and they result in a lot of days away from work, especially for people who move heavy objects using their body. On average, you can see about 12 days away from work, and for a single sprain or strain, the medical bills, time away from work, and legal bills can be up to $95,000 on average for just a strain or a sprain. So this is an important problem that there's a lot of work being done. And we estimate $13.3 billion in direct costs from these musculoskeletal disorders. So one potential solution for this type of a problem is to automate the task. So to replace the people in the workplace with robots that can do the job of the workplace. This requires a lot of reorganization of the area, potentially like a closure of the site for a long time. You have to really change the way that you do the task in order to allow robots to do it, and it's very expensive. And even if you succeed in fully automating the task that people were working on, it's pretty likely that there will still be people involved in these activities. And there are a lot of tasks that people are really good at that robots aren't. So tasks that require physical or mental flexibility especially are difficult for a robot to perform. So we believe that you'll always require at least some people to be in the workplace in these sort of manufacturing environments. And so there's a lot of motivation to improve the safety and reduce the effort of these people working in this type of a field. So one potential solution to make it easier to do this type of job while a person is still in like the manufacturing line is to use assistive devices like exoskeletons. So most of the devices that are on the market are what we'd call a passive device. So you can see an example on the left here. This is actually a commercially available device, and it is used in some factories in the real world. There are also similar devices for the upper limb, for mainly supporting the back, the hips. They also make them for the knees. And you can see here, this is basically just a spring. So as you squish the spring, it assists you more and it helps you kind of bounce back up. So these passive devices, which do not have any motors or electronics, there's no active assistance, they're just based on springs and dampers, basically. So they're very predictable. They don't have as many parts that can break. They don't require charging batteries, and they don't require controllers. So there are a lot of pros of a passive device, but there are also cons. So these are kind of simple devices. They usually have one function. Some of them have like a clutch that you can enable so that it can support you during some activities, and then it can be disabled while you're walking around. But especially during other activities, it can be really difficult. For example, with this device, it is hard to sit down. It could be hard to operate like a vehicle. It could be hard to run away if you were like in an emergency situation. So there are pros and cons. These are really good at some activities, but not necessarily all. On the other hand, powered devices or active devices, they are really versatile. So these are going to be using motors and batteries and computers to do a similar thing, where we're going to be providing some assistance, very similar to how the passive device would work. However, instead of just basing it off of a mechanical component like a spring or a damper that has a really defined assistance profile, powered devices can be programmed to provide assistance in a lot of different ways. So some of the ways that we control devices are, for example, we can look up what the torque from a human knee would be during an activity, and we can just tell the robot to do some portion of that, follow basically the same trajectory. We can tell it to look at, say, the knee angle and provide some assistance based on the knee angle. That's another example. So there are a lot of ways that they're much more flexible in their controls, and you can use them to identify an activity. So for example, the robot could identify that you're lifting and lowering a box, and then it can identify that you want to walk and switch to a different controller that would enable that other activity. Of course, there are some cons for this as well. You need to charge the battery, you have to program a controller, and you hope that that controller is intuitive and that people will want to use it. So there are pros and cons to passive and powered devices. In our lab, we focus mainly on powered devices. And so in this study, I'll be talking about powered devices, which use a motor to provide assistance. So in this study, we used 2 copies of this powered knee exoskeleton during an occupational lifting and lowering task. And we did look at lifting and lowering. I'm going to focus in this presentation on the lifting movement, but we saw similar results during the lowering movement as well. And specifically, we were looking at how the exoskeletons affected the muscle activation in the quadricep muscles and also how it affected full body biomechanics. So in the past, people have looked at robotic knee exoskeletons and passive knee exoskeletons during lifting and lowering tasks, and they looked only at muscle activation. They didn't actually perform full body biomechanics, so they weren't able to look at how all of the different segments and joints of the body were interacting and how it affects the internal torques of the person. And so that is the really novel part of this study, is that we did perform full body biomechanics. Okay, so we'll look first at our study design. So in this study, we had 8 healthy subjects who participated. They lifted and lowered a 9-kilogram box, and they performed more than 10 lifts, actually. They performed like 12 to 15 lifts, and then we used 10 lifts per subject for the analysis. And so all the figures that you'll see in this presentation will be averaged across 10 lifts per subject. And then we had 3 conditions. So we had a no exo condition where subjects lifted and lowered without wearing the exoskeleton at all. We had a condition called exo assist, where the exoskeleton was providing assistance to the user, and I'll talk more about how that was controlled in a moment. And then we also had this no assist condition. So in the no assist condition, the robot was worn, but it didn't provide any active assistance or resistance. In fact, we programmed it so that it would compensate for its own inertia, which just basically means it tries to get out of the way. So it tries to have the least amount of resistance and just move with the person without providing assistance or resistance. And so we had these 3 conditions. They lifted 10 lifts per condition, and we also had them pause in between. So here's a video. So we have them pause at the top and bottom, and that's mostly for data analysis purposes. It's much easier to break this movement up into chunks if there's a little pause in between. And we also want to make sure that the subjects have time to stabilize themselves at the top and the bottom. Okay, so now I'm going to talk about the exoskeleton controller. And this is the controller for the exo assist condition. So this is how it was controlled when it was actively assisting the users. And how we did it, we programmed it to be a virtual spring, which means that the motor kind of pretends that it is a big spring at the knee, where it's always providing extension torque during both the lifting and lowering position. So this equation right here shows the torque. So this little t is a torque at the knee. And we define it as K, which is a stiffness, which is like how basically stiff is that virtual spring, how hard is it to compress. And then this is just the equation for a spring torque. So we take the measured knee angle and we subtract the equilibrium position of the knee, which is basically where that virtual spring wants to sit. So where is it most, like if you just let that spring go? Basically, where would it want to be? And the spring will always be pulling the knee back towards that equilibrium position, which we set to 15 degrees of knee flexion. So close to the top of the movement, but not completely extended. Okay, and then we had it turned off during that top portion of the movement. So when you were lifting and you got almost all the way up, it would stop pulling you up, it would stop assisting you actively. And we did that because people had a hard time stabilizing themselves at the top of the movement when the exoskeletons were assisting. So we did a lot of pilot testing, and subjects had just problems. They were kind of fighting the assistance at the top of the movement, mainly because you don't need a lot of torque at the top. You're mostly balancing and stabilizing yourself. And then similarly, at the beginning of the lowering movement, we also had it disabled at that top little chunk. So this controller, basing it off of a spring, it was not super exciting. We tried some more, like some cooler controllers, such as a biomimetic torque profile, similar to what a human knee would be doing during this type of a movement. And we found that this virtual spring was really nice. First, because it's really predictable. It gave us the kind of the profile of assistance that we were looking for, and people found it very intuitive. So this is the controller that we ended up with. And before I move on, I'll just say this is the knee is less than 15 degrees, so more extended than 15 degrees, the torque is just 0. So that's just saying the spring was turned off at the top of the movement. Okay. So now let's talk about instrumentation. So how did we actually record this movement? What things were we looking at? First, we have all these little reflective balls on the person. And unfortunately, I didn't take any pictures where you could see all the cameras, but these cameras, we had 19 cameras all around the edge of the room along the ceiling, and they're pointed at the area where the people are doing the lift. And these cameras are sending out LED light. It bounces off these reflective markers and it bounces back to the cameras. And so by doing that, we can look at just the marker positions, just these little balls, and you don't see, it's not like a video. So I'll show you a picture of what is being seen by the motion capture cameras in a moment. But this is the same technology that they use for a lot of animation. So if you've seen like Avatar, they use motion capture. Another cool thing is they'll do motion capture with a bunch of little balls on people's faces for movies. That's sort of a newer technology. But the data capture is very similar to what is used in movie industry. And this allows us to track the movement of the person in space. We also have instrumented force plates. So these force plates, we have one under each of the subject's feet and one under the box as well. And what you can do when you combine motion capture with force plates is you can go back and calculate the torque at each joint and the power at each joint. So you can look and see how hard is the ankle pushing off, how hard is the knee extending. And it's almost like magic, like you can see what's going on inside of people's joints. This is what I usually do, and I just think it's so cool. I hope you think it's cool too. Okay, we also record surface electromyography. And so electromyography means we're measuring the electricity in your muscles through your skin. So when you contract your muscles, it creates a little electrical current that can be measured through your skin. And this is pretty much proportional to how hard your muscles are contracting. And so in addition to the joint torques that we can find through motion capture, we can directly measure how hard certain muscles are contracting and how hard they're working. And so we added these electromyography sensors to the vastus lateralis and vastus medialis, which are two of your quadriceps muscles. They both perform knee extension. And so these are the muscles that are kind of most active during both lifting and lowering. And I should point out that during the lowering task, even though you're moving in the different direction, it still requires extension torque. It still requires the same quadriceps muscles to be contracting, but it's actually contracting in an eccentric way. So when you lift, your muscles are contracting and you're lifting yourself up. That would be a concentric contraction. In an eccentric contraction, you're doing a controlled lowering. So your muscles are lengthening as you're going down, but it's still the same muscles that are working hard. It's the same kind of a torque. You're just doing it in the opposite direction. Okay, and then we also recorded the knee exoskeleton data. And the part that we'll talk about the most is the assistive torque from the exoskeleton. So we take the torque that the exoskeleton is providing, and we'll use that to help us figure out how much work the person is doing versus the exoskeleton, which I'll discuss later. Okay, so here is a view of our software, and it gives you a better idea of the kind of modeling that we're doing. So on this side, we have a subject with the little dots. And then in the center here, this is called Vicon Nexus. And in this program, we go through and identify each of those dots. So the program knows the name of each dot and how it relates to the other dots. And so this program will allow us to identify and track those marker positions through space. And then over here, we use that to build a biomechanical model. So we're using simple shapes like cylinders and cones and spheres to model the human body. And this is both a kinematic and a kinetic model for the most part. So all the human segments that you see here have both positions and they have force interactions with each other. And you can see these bones here. These are the exoskeleton models. So we did track the exoskeleton and the box. I modeled them as bones because I like how it looks, no specific reason. And so this will allow us to actually perform calculations. One more thing I should point out before I move on is that we tracked the thorax segment, the abdomen segment, and the pelvis segment separately. So in the majority of motion capture, well, I'd say a lot of people don't even do upper body motion capture, but when they do, they'll often use the thorax and abdomen segments as just one long segment. So just a solid chunk. And by splitting it up like this, it allowed us to do some exploratory analyses of the trunk angles, which I'll talk about at the end. Okay, talk briefly about the study design. So as I mentioned before, we had 3 conditions: no exo, no assist, and exo assist. We had 8 subjects doing 10 repetitions each, and we averaged those subjects across subjects. So we took all 10 repetitions per subject and averaged them. So we have one line or one value per subject, which then we would average across the 8. So when you see plots in this presentation, there'll be the across subject means and standard errors. The outcome measures that we were most interested in were, first of all, those EMGs. So we looked at the peak, which is the maximal effort, basically, as well as the integral, which is the area under the curve, which represents like the total amount of work that was required to do a task. We also looked at the peak biological knee torque. And for the EMGs, we did it for vastus medialis and lateralis on the right and left side. So for each of those outcome measures, we did statistical testing. Because we had 3 conditions, we did a repeated measures ANOVA. So the ANOVA will tell us whether any of those 3 groups are significantly different from any of the other 3 groups. And repeated measures means that each subject is kind of their own control. So because each subject performed all 3 conditions, it is a different type of statistics with a little bit more power. So before we ran this ANOVA, we tested the assumption of sphericity, and if it was violated, we applied this statistical correction. And then if the ANOVA was significant, then we performed post hoc analysis that allowed us to identify which groups were actually different from each other. So now we'll start talking about some results, the exciting part. And we'll start with the electromyography because it was one of our main outcome measures. And before I hop in here, let me describe the axes that we're looking at. And this will be very similar to what you see in the other plots. So on the x-axis here, we have lift completion. So 0 means that's when the movement started. That's the start of the lift. So they're at the bottom, they're squatted down. This little person shows you where they are. And then at 100, they are fully stood up. And we've zoomed out a little bit to show a little chunk of time before the movement starts and after the movement ends. And we do that because there are sometimes anticipatory movements before the movement starts, and at the end, there are sometimes stabilization movements. And it can just be really helpful to see that and just have that information so you have context. But the movement is happening between 0 and 100%. And then on the y-axis here, we have the EMG. So this is a normalized voltage, and this represents how hard these muscles are contracting during the movement as a percent of the lift completion. So the vastus lateralis, you can see, let's look at the 3 lines. So no exo is the black line, and it is the highest contraction of this muscle. When we look at no assist here, it's the dotted gray line, very similar to the no exo. And then the red is the exo assist. So the main comparison in all of these that we're interested in is the no exoskeleton versus the exo assist condition. And as you can see, there's a really big reduction in all of these muscles when people use the exoskeleton. So that's a really good result. That shows that these muscles are not working as hard when people are using the exoskeleton and it is assisting their movement. So then we pulled out some metrics, and we'll look right here at the peaks. So these are shown as a percent change from no exo. And so when you look at these bars, a positive number means that it slightly increased compared to no exo. So in this example, this little plot, we see that on average, the no assist was a tiny bit harder than no exo, but the exo assist was much easier, or some amount easier, this amount easier. So you can see these negative bars are showing a decrease compared to no exo condition. And when we did the statistics here, we found that 3 of these muscles were significantly reduced compared to the no exo condition. And here I'm only showing the statistics for no exo versus exo assist. So that's our main comparison of interest. And when we look at that comparison, we see the 3 muscles that reduced their activation significantly. On average, it was about 30%. So that's a big reduction. That's meaningful. When we looked at the integral, we didn't actually find any significant differences. So that's kind of interesting. You kind of expect that when the peak goes down, the integral will be doing something similar. But one thing that time-based plot, or let me show you, that this plot doesn't show is the actual time it took to stand up. And so because we've normalized between 0 and 100%, it's hard to tell, but the exoskeleton condition actually took longer. So people moved more slowly and lifted in more time. They took more time to stand up with the exoskeleton assistance. And so that is one reason why we think the integral results were a little different from the peak, is because the integral takes into consideration the time it took to get up. But you can also still see that there is a reduction between the no exo and the exo assist for all of these muscles, but the results were much more variable. So you can see the individual subject dots, there's a good spread there. So not every subject responded in the same way. Okay. Next, I want to talk about how we estimated the biological knee torque. Because when we get torque out of motion capture, we get what's called a total torque. So the exoskeleton and the person's leg were both connected to the same force plate. They were both standing on the same force plate. So the right leg and the left leg had their own force plates, but the exoskeletons didn't have a unique force plate from that, if that makes sense. And so the way that is done in our field, this is the standard in our field way to estimate it, is we take this total torque coming out of motion capture, and we take the exoskeleton torque that was provided by the knee exoskeleton. So this is what the robot was contributing to the movement. We subtract the exoskeleton torque from the total torque, and that leaves us with the biological torque. And so this estimate isn't perfect, of course. It is going to underestimate the biological torque by some amount, and we do realize that, but it is the way that the field has decided to do it, and until someone comes up with a better method, we're going to keep doing it. So this is how we calculated the biological knee torque and biological knee power. And I just point out that we included the EMGs just to validate that there is a good reduction. So because we see a reduction in the EMGs, we can say this reduction is real. We just don't know how accurate the biological torque estimate is because there's some unmodeled loss between the exoskeleton and the person. Okay, so now we'll look at the joint torques. Let's start. So the overall vibe here is that all of the peaks decreased with the exoskeleton compared to the no exoskeleton, but there were differences across joints, of course. So this one is our most interesting, or the one that we were most focused on for our analysis because it was a primary outcome measure, is the biological knee torque. And so you can see that that biological knee torque was much less. It's a little weird because it's a negative number, but this is a smaller negative number than the no exo or no assist condition. And it was 53% lower with the exoskeleton, which was a significant difference. So this is very exciting, of course. No one was able before now, because they didn't perform motion capture, to estimate this at all. And so this is very exciting, but something that we weren't looking for and we were even more excited about, at least I was, is that we saw a reduction at the ankle. So this exoskeleton didn't assist the ankle directly. It only assisted the knee directly, but it did connect to the shin, and there was a foot plate in the shoe. And also we have the human in the loop is what we call it. So the human is a part of the system as well. And when we assist the knee, the person is also reducing the amount of work that they're doing with their ankle. And so this was sort of like a collateral finding, but it was very exciting and hadn't been shown before. We've seen reductions at other joints when we use exoskeletons, but this specific configuration had not been shown before. And then we also see very small reductions at the hip. But what we're looking at most here is we don't want to see an increase. So we didn't see an increase at the hip, and that's a great result. We don't want to see, and what sometimes happens is an exoskeleton will assist one joint and you'll see really good results for, say, the knee, but then you look and the hip is doing way more. That's not what you want to see, and that's not what we saw here. So this suggests that there is not very much compensatory there's not very much compensation happening. The joints are mostly moving. At the hip, it's very similar with and without the exoskeleton. And at the ankle, we saw a difference, but it was less work at the ankle with the exoskeleton. Okay, so this is a summary of the primary outcome measures. First, we saw a significant reduction in the EMGs of the quadriceps muscles and a significant reduction in the biological knee torque. And we also saw reduced ankle torques, although it was not a primary outcome measure, so we don't know if it would be significant. Okay, so now we're going to go into some secondary outcome measures, which help us understand what's happening on a full body level, but we didn't run statistics on them. They're still an important part of the study, though. So this first one is joint angles. So we're looking at the angle of these three joints, the ankle, knee, and the hip. And what we see is that there is a slight reduction in the range of motion with the exoskeleton compared to the no exoskeleton. And again, what we're looking for here mainly is to see whether there was a lot of compensation. So we do see a slight reduction, but we don't see big changes in these angles during the movement, which is positive. And we did also check whether or not this decreased range of motion could have been attributed to the range of motion of the exoskeleton. But we did check, and these movements were within the range of motion of the exoskeleton. So we don't think people were hitting the end stop and like not able to keep going, for example. Now we'll look at the joint powers. And so if we look at the top here, you can see that the ankle power is lower with the exoskeleton, and it's really a lot lower at the knee. So we see huge reductions at the knee, small reductions at the ankle, and small reductions at the hip. So once again, this is showing we don't see a lot of compensation, and we do see reductions with that exoskeleton. Okay, so now another part of the study that was kind of unique compared to other studies was that we modeled the upper body and we modeled it with multiple segments. So we were able to look at the thoracic joint, which is the joint between the thorax and the abdomen. And we were able to look at the lumbar joint, which is the joint between the abdomen and the pelvis. And so here are those plots. We calculated the angles, the torque, and the power of these two joints. So we have lumbar on the left and thoracic on the right. And if we start off by looking at the angles, we see a little bit of an increase in the range of motion with the exoskeleton. And so this is another thing we were worried about is if we assist the knees, are we going to really change the behavior of the back? And we see this slight increase in the range of motion. So it's definitely worth looking at more. And we think that this should be a focus of future studies in this area. But when we go down to the torque, so like this increased angle, it's small, but it is like we should look at it, right? But when we look at the torques, we don't see meaningful changes at the lumbar and thoracic torques, which is positive from our perspective. So we're not seeing big changes, increases or decreases, which means that in theory, these torque, like the behavior at the back is not a big difference. There's not a big difference with the exoskeleton. But I will point out that this is a bending torque around these joints. And so the type of modeling we use is unable to calculate contact torque or contact forces. And so the compressive forces in the back are not modeled, but it is possible with other programs. And so that would be really interesting to look into in the future. And then we do also see the lumbar and thoracic joint power increased a little bit with the exoskeleton, which suggests that these joints were actually moving a little bit faster with the exoskeleton. And this makes sense. We saw that the lower limb joints moved slower with the exoskeleton, and so they're just completing this movement a little bit quicker, which results in an increase in the power. So power is torque times angular velocity. And so that's how we get an increase in power without an increase in torque. So overall, these results are not very, they're not concerning. It doesn't say the back was working much harder. It says the back was working pretty similar with and without the exoskeleton, and more work should be done here. We also looked at the trunk angle in the lab frame. So this is something that other studies look at more often because you can measure these with just an inertial measurement unit. So you can take a little wearable device without performing full body motion capture and get some information out. So we replicated those kind of measurements just for comparison, and also because it's good to know. You want to see how the person is behaving with respect to gravity, basically. So this first one is pitch, which is anterior and posterior. I made this kind of ugly diagram here to help you see what a pitch is. So this will be anterior lean and posterior lean, or forward and backward. And very minimal changes here. So we see a tiny increase with the exoskeleton in this anterior lean, but on the whole scale of this graph, it's not a big difference. When we look at roll, so this will be leaning side to side or tilting side to side. This looks like a big increase, but if you look at the scale, it's very small. So at the start of the movement, people were leaned a little bit to the left, tilted a little bit to the left. And then at the top of the movement, they were more centered. And that was true across conditions. And then similarly in yaw, which is a vertical rotation. So sorry, that was kind of confusing. It's like a spin or a left rotation or a right rotation. So in the yaw plane, once again, we see a little bit of left rotation at the bottom of the movement, and then they end up more centered. And when we were looking at this, it was kind of confusing. We were wondering, like, why is there this side change? You know, why are they tilted and rotated more to the left? And I think it's because all the subjects were in the same position, and we were over on their left side saying, stand up, down, up, down. And so I think when people were at the bottom, they were sort of tilted over, kind of waiting for our cue. That's my theory. But these differences are really small. So it's worth looking more into and potentially randomizing the side that the person cueing the subject sits on. But overall, nothing too remarkable here. Okay, so our secondary outcome measures show there's still work to be done when we are trying to understand the joint range of motion, joint power, and how the back segments are relating during this type of an activity. So there's definitely room for more work, but we definitely saw positive improvements with this device. So to conclude a little bit, we had 8 subjects perform lifting and lowering tasks with this exoskeleton, and we saw that with the exoskeleton, people had lower muscle activations. So their muscles were working less hard, at least their quadriceps, and we saw a reduction in the biological knee torque peak. And so together, these say with pretty good certainty that this exoskeleton reduced the effort needed to perform this kind of a lift. And so in the future, some things that we could look at, one thing I wish we'd done was record EMG from more muscles. So we couldn't really see co-contraction. A lot of times you'll have muscles in a flexion and an extension muscle. They're contracting together to stiffen the joint to stabilize the person, and we call that a co-contraction. And so that's something that we weren't able to capture that could be really interesting in the future. And then, of course, we need to extend this work to more realistic environments. So a lot of exoskeleton research, you either see laboratory work or field work, because in the laboratory, we can do a much better measurement. We can measure motion capture. You don't have motion capture in the workplace. But in a lab environment, we can really precisely measure the position, measure the forces and the torques, and measure EMGs, so that's a big advantage. But before this could be used in the workplace, we definitely need to see how it would behave in the workplace. Some other future work is to extend this to other controllers. So we really only looked at lifting and lowering in this study. But if it were to be extended to a real workplace, you would definitely need to have activity identification and work in some walking controllers and sit to stand controllers, for example. Okay, thank you so much. Thank you to my lab and all of our funding sources. I also wanted to mention that this work was done with another Rocky Mountain Center student. She was a master's student, and this was her master's project. This is Margaret. She is looking for jobs right now, so if you're looking to hire an excellent mechanical engineer, here's her email. And here's my email in case you have other questions after this presentation is over. So with that, I would love to take some questions from the audience.
Thank you, Grace. Like you, I find this work fascinating and super cool, and I appreciate the plug for Margaret. That's very nice. So we do have a few questions that came in, and I invite the rest of you to submit any questions you have now into the Q&A box. I'll just bring these to you in order.
Okay.
Are those devices part of a comprehensive safety management system as a temporary fix for ergo hazards, or would they be considered meant more for a permanent PPE control?
That's such a good question. Sorry, could you read that one more time? What were my
Absolutely.
options?
Absolutely. So introduced as a comprehensive as part of a safety management system as a temporary fix for ergo hazards, for example, or are they meant as a PPE? So it's really, yeah,
Yeah,
PPE or
that's a
not.
great question. I am not totally sure how people would implement these in the real workplace. That I would say is above my pay grade, but I would expect that they would be more of a comprehensive plan. So when people like in workplaces that use exoskeletons, they're mostly passive, but in general, they are given to workers for everyday use and kind of with the intention of them using them over time. But it could be used to definitely, if there was like a specific risk, I could see that as a good application as well.
Got you. Here's a direct reference to slide 22. The knee torque started negative and ended positive. Can you explain that?
Yes, let me go back to that slide. Yeah, so it starts off as an extension torque. So at the start of this plot, they are squatted down and you have a really large extension torque to just keep yourself in that position and then to initiate the upward movement. And as you get to right here, it actually switches to a flexion torque. So as you're going up, you have inertia, or momentum is another way to think of that. So your whole body has inertia and momentum. And as you get partway up the movement, you start actually contracting to flex your knees to resist that extension and slow yourself down. So if we looked at velocity, which I don't have a plot of, but the velocity would be highest in the center here, and then you're slowing yourself down. So eventually you are not moving at the top of the movement. And so this flexion torque is here to slow yourself down and also to stabilize.
Excellent. Can you talk about how these devices might prevent musculoskeletal injuries with respect to specifically to repetitive motion? Is this just a delay for getting repetitive motion injuries, or can this actually prevent them?
That's a great question. Yeah, so we envision these as a solution or, something that would help reduce the load on your joints during these overuse. So it would prevent an overuse injury potentially. It would be reducing the load on your knees during every repetition over time. And so it would be resulting in like lower knee torques every repetition in theory, which could prevent knee injuries. So it could prevent a knee overuse. Another thing that we were looking at in this study is another goal of this study is to allow people to use a knee-centric lifting form for longer. So a lot of times people will recommend a knee-centric lifting form with really high knee extension to reduce torques at the back. And that's exhausting. Knee-centric lifting is more difficult. It requires higher torques. And so a lot of time, as someone is lifting over and over again over an extended period, they will start to change from a knee-centric lifting form to a back-centric lifting form, increasing their risk. And so another potential benefit of this technology would be to allow people to use a knee-centric lifting form for longer.
Got you. You ever investigate the possibility of a unilateral approach, or would these always be intended to be applied bilaterally?
I think in an occupational setting, it would always be bilateral just because people are approximately equally strong on both sides. I could see a unilateral application if you were doing an asymmetric task, for example, that could potentially be helpful. Or if a person had an existing injury, potentially to assist their injured leg more than their uninjured leg. But in rehabilitation settings, which is how we do a lot of our research, we do a lot of research with stroke and amputees. And so those injuries are, for the most part, unilateral. When you have a stroke, usually one half of your body is a lot more affected than the other half. And so in those situations, we'll often use unilateral assistance.
Got you. Got some more questions coming in. What worker population or job task would you recommend having this type of exoskeleton be applied to?
I think it would mostly be people who are doing manual lifting tasks, just because it is a knee exoskeleton. I've also seen for those passive exoskeletons that support the trunk more, it can help people maintain a leaned over posture. But yeah, I think with this knee exoskeleton, it would mostly be for people who are bending down, lifting things up and putting them somewhere else. So
Got you.
manual material movers.
Thank you. And how much does the device weigh?
Oh, excellent question. I printed it out. 2.6 kilograms per side, including the battery, electronics, and physical interfaces.
Oh, that's pretty good.
It
Are
is
there
pretty-
specific guidelines that should be followed if we're looking for similar devices, specific things we should look at before acquiring something like this?
Yeah, for sure. Um, I would definitely look into like the safety. You want to make sure that these motors are not going to be like overextending the knee. So that's definitely one concern, is that you can move people into worse positions potentially. So a safety concern, the intuitiveness of the controller, the ability to switch modes and how accurate it is as switching modes. I'll point out this type of powered exoskeleton isn't available on the market yet, but we're potentially going to collaborate with Ottobock in the future. So it's possible. I'm sure that there are like other regulations from the government too.
Got you. Did you do any qualitative ratings, surveys such as comfort wearing it, ease of lift, negative consequences to the back or shoulder, anything like that?
We did not in this study, but in the previous version of this exoskeleton, so this is the second generation that was used in this study. In the previous generation, we did look at, we used the NASA TLX score, which looks at how difficult it is to perform a task like mentally for the most part, and then also comfort ratings. And so we've looked at that in some previous studies, but we didn't do it for this study. Great question.
Okay, next question. Thank you. Next question. Were participants instructed in proper power lift position?
So we didn't specifically instruct them on how to lift. We mostly, well, let me step back. So before the experiment day, at least one day before, we had a training session where they lifted the box with and without the exoskeleton just to get used to it and so that we could see how deep they squatted naturally. We didn't instruct them on how to power lift, but they did all have, like, they naturally all had pretty knee-centric lifts. So we were pretty happy with their initial natural squatting form. One type of feedback that we did give people is if they squatted really deeply, like, so our exoskeleton can only bend to 110 degrees. And so if the person naturally wanted to squat to like 120 degrees, we asked them to squat less deeply. And then we kept an eye on it during all the conditions, just to make sure that we were doing approximately the same type of a movement during all the conditions.
All right, excellent. Next question. Given the reduction in joint forces and EMG that you saw, how would you approach conducting a risk assessment using traditional ergonomic assessment tools if an employer was to implement this device as a permanent control measure?
That's a really great question that I don't really know how to answer. That's not my area of expertise. I apologize.
That's fair enough. Let's move on. Next question. Any qualitative work to determine the perceived or metabolic fatigue when using the device? I think that we sort of touched on that as a no. Is that correct?
Yeah, that's correct. And usually, like, we do a lot of metabolic testing. We haven't actually done it for this type of an activity because usually you're looking at like several minutes up to 6 minutes of sustained activity before you can reliably measure metabolic effort. Um, but that would be very interesting to do in the future. And I bet people have modified metabolic procedures for, non-steady state movement. So usually we look at metabolics during walking. But I'm sure someone has figured out how to modify it for like a lifting activity. So that would be super interesting. I think you'd have to control like their speed and cadence a lot, but yeah, that would be exciting in the future. We didn't do it here.
Okay. We've got time for a couple more. Did you look at or measure changes in center of gravity?
We measured it. We didn't really look at it. We did look at it just to make sure nothing funky was going on, but it wasn't one of our main areas of interest.
And are they easy to put on? Could a worker do it on their own, or would they need sort of oversight training, perhaps?
That's an excellent question. I think they would probably need training. It's pretty easy to put on yourself if you're sitting on the floor. Let me go back to a picture of the EXO. Doo, 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 doo. So there's a foot plate that goes inside of your shoe, and then yeah, let's go here. So there's a foot plate inside of the shoe down here, and then there's just straps at the shank and the thigh. And so when we were getting people into these, we sat them on a bench and kind of held the exoskeletons while they were putting it on. But Margaret, while she was figuring out controllers, she was putting them on by herself all the time. So it's totally possible. It's just a little bit awkward because the mass is more located at the top of the device.
Thank you. And will you test these devices on 45 to 60-year-olds who generally have reduced whole body range of motion?
That would be really awesome. I hope we do in the future. The population that we chose for this study were all graduate students, so it was a convenience sample of people who were available to us. But I think in the future, definitely at least looking at more of a realistic population would be really helpful.
Okay, let's see. Could this EXO be used in foot pedal tasks like fork truck, large vehicles, etc.?
Yeah, that's a great question. I think it wouldn't impede it. When it's turned on into transparent mode, there is a free hinge at the ankle. And so when it's in transparent mode, it just moves with the person and gets out of the way. I wouldn't expect there to be any problems operating a vehicle using this device, but I haven't actually tried it myself.
Got you. Any pitfalls you see of using cautionary tales of using a device like this?
Yeah, that's a great question. Generally with robotic devices, it's really important that you get the activity classification correct so that the person and the robot are kind of on the same page and that it's intuitive. So for example, if the robot thinks you're about to do a squat, but you actually want to go walk somewhere, it can behave really strangely. And honestly, that's a huge problem when you're trying to put it into a workplace. I know that's true for the passive exoskeletons, is like if something works wrong like a couple of times, especially at the beginning, it can really impact the acceptance of that device in the workplace. So I'd say the controller is a big one, getting an intuitive controller. That's my main.
Okay, and finally, we have time for this last one here. Will you test the devices on people who have experienced prior knee injury?
That's a great question as well. So we have tested this device on people who have had a stroke with some really positive results. And so I would expect it to work very similarly. And we're interested in like ACL populations and other musculoskeletal disorders. So I hope we do that testing in the future.
All right, well, thank you. Grace, we've run out of time. I just want to thank you very much for your expertise.
Thank you so
Uh,
much. This was great.
Learners, you can learn more and register for our upcoming events at coeh.berkeley.edu. You can also subscribe to our YouTube channel where you'll find previous recordings of our webinars. Don't forget about your registration email and get your fill out your evaluation form to get that CE continuing contact hour. Several people did ask if they could get material emailed to them. We can put together a PDF deck, and you can email us at coehce@berkeley.edu. That's coehce@berkeley.edu. So if you have any questions for us, feel free to just ping us via that email address. Again, you can request the PDF there. And thank you, everyone, for joining us, and especially a big thank you to Dr. Hunt. That was an excellent
Thank you so
presentation.
much.
We'll see you next time. Bye-bye.